Ian, you had a couple of sessions here at POWERGEN Europe talking about Power-to-X, hydrogen, ammonia. Why is Power-to-X so relevant for decarbonisation?
So decarbonisation it's really one of the challenges of our time. How do we decarbonise our energy industries?
Yep.
Energy is a good thing. If you think about quality of life, so much of what makes you have a good quality of life, it depends on access to affordable, abundant energy. So that's not going to change. We're going to want to still have access to the energy systems as we do today. The difficulty is that our energy systems are very much based on fossil energy sources with the CO2 emissions that come from that and the consequences for climate change. So decarbonisation is a really important topic in its own right. And the Power-to-X part of it really talks about, so when people talk about Power-to-X, what they often mean is generating hydrogen from renewable energy sources.
Yep.
And that then gives us another way of storing and transporting energy other than as electricity. So we're all familiar with solar PV and wind farms and other sources of renewable energy, and if they're connected to the grid and you can put it into the grid and use the energy straight away, that's great. You can use batteries to store it and use it at a later time, but quite often you see a geographic separation between where the power is produced and where you want to consume it.
There's no transmission line in between or whatever, right?
Yeah, exactly. Particularly if there's a sea in the way, often you get interconnects, but you can be somewhat further apart. And some of our industries are quite difficult to decarbonise with electricity on their own. For example, the transportation industry at the moment uses entirely a chemical fuel, petrol and diesel. Aviation is the same, that's very difficult to decarbonise for that reason. Heating is another big user of, exactly. So natural gas is the big one, certainly in Western Europe and across the world. And actually electricity, so if I take the UK as an example, electricity generation is sort of 20-25% of the energy we use as a nation. The other 70-75% is transportation, heating, as I mentioned, industrial users of energy, and they're almost entirely fossil-based today. We're actually making quite good inroads into decarbonising electricity generation. So half our electricity in the UK is low carbon already, we're doing pretty well there. But transport and heating, entirely fossil-based still, it's really hard. So this Power-to-X idea is using renewable sources to produce hydrogen that can then start to displace some of the fossil energy sources that are elsewhere in our energy system.
Now, one of the challenges with hydrogen is getting enough of it into the right place at the right time and storing it, and there's all sorts of creative ways and means, but where's that headed?
Exactly. So hydrogen's a great fuel. It contains a lot of energy, and its emissions are very low. If you run it through a fuel cell, you just get heat and water. The combustion products again are just water.
Yep.
So it's got a lot of potential as a carbon-free fuel. The challenge with hydrogen is it's very hard, and by that I mean expensive, to get in one place. If I take fuel cell electric vehicles as an example, so a fuel cell electric vehicle will have a range of 300 kilometres or so.
Yep.
So getting a good range with a fuel cell EV is readily achievable, and the way they do that is to use hydrogen, but they have a very high pressure fuel tank.
Okay.
So an EV will have 3 or 4, maybe 5 kilos of hydrogen on board, but it's stored at 700 bar, because that's the pressure you need to go to get 700 bar. That's the pressure you need to get the fuel tank, to a reasonable size.
Otherwise, it's the caravan out the
Otherwise,
back.
it's just huge. Yeah, exactly, and it becomes impractical. And if anything, if you want to use hydrogen to power a gas turbine, for example, or as an industrial heat source, then that problem is many times worse. You just can't have large-scale tanks at 700 bar. It's impractical. The walls get too thick. So storing a lot of hydrogen, or storing enough hydrogen in one place to be useful from an industrial context point of view, is challenging. So you can use salt caverns, for example. They're quite good. Hydrogen pipelines, large underground storage potentially. They're great if you have them, but
not every place in the world has a salt cavern.
And this is it. So then we start to think about, well, how can we overcome this challenge of, we talk about volumetric energy density, so getting a lot of hydrogen in a small volume is the difficult thing. And you can overcome that by using a hydrogen carrier.
Okay.
And of course, in some ways that's what we do today, except that the hydrogen carriers we use today are hydrocarbon fuels. So life gets a lot easier if you hang the hydrogen atom off a carbon atom. And then you have petrol and diesel as a liquid fuel, and you can ship them around in tankers and stir them, and that's how it works. And it works brilliantly, apart from the CO2 emissions associated with burning that fuel. So liquid fuels are a very good way of storing and transporting energy. So wouldn't it be great if we could make a liquid fuel, a hydrogen carrier from renewable energy? And this really is the sort of the next stage in the Power-to-X story. And there's a number of possible molecules that you could use. Yeah. Some involve carbon, some don't. So you can synthesize synthetic natural gas. So this is where you take CO2 from another existing emission source.
Coal-fired plant or whatever, right?
Yeah, exactly. And combine it with the hydrogen from electrolysis, and you can make synthetic natural gas. You can also make higher hydrocarbons through Fischer-Tropsch synthesis. So you can even get up to petrol and diesel type molecules.
Yep.
DME, is a good diesel substitute. Methanol is another carbon-containing candidate that's got a lot of attention, including within Siemens. And then what I've also been talking about here at the conference today, and I gave a talk earlier specifically on the possibilities that ammonia presents us with. And ammonia is attractive for a number of reasons, chiefly because it's carbon-free. So you can synthesize ammonia by taking nitrogen from the air.
And there's a lot of that around?
And yeah, exactly. So the atmosphere is about 80% nitrogen, so it's very abundant, and actually it's pretty easy. It's low cost, it's cheap to separate.
To pull it in, that's it.
Yeah, exactly. It's an industrially standard process. It doesn't take too much energy to separate nitrogen from the atmosphere. And then you can hang the hydrogen molecules off a nitrogen atom, that's an ammonia molecule. And then ammonia has a very high hydrogen density, so about 17% of ammonia by weight is hydrogen. And that's actually, so if I had a litre of liquid ammonia, that would have more hydrogen in it than a litre of liquid hydrogen. But a significant difference is that liquid hydrogen is a cryogenic liquid, so you have to get hydrogen down to 22 Kelvin. Yeah, so minus 250 odd.
To do it anyway, right?
Exactly, yeah, and then you have the ongoing refrigeration cost. So ammonia gives you a practical way of storing and transporting hydrogen. So it's really a way to think about it is that it solves the storage and distribution problem associated with hydrogen in a way that's technically mature, because the ammonia industry is very mature already today.
Now, one of the questions when it comes to ammonia, people would say, but ammonia is in the bag of fertilizer. Is that what you're talking about? But there's other ways of storing ammonia, or is it liquid, solid? How is it?
So, yeah, you're absolutely right. The world makes something like 180 million tons of ammonia a year. So it's a very significant industry, and that's advantageous because we can piggyback off that, all those mature supply chains.
Already,
yeah, exactly. Right? We know how to produce it in bulk at a low cost. The technology we need to do that already exists, and we can just repurpose. I often talk about innovation, not invention. I haven't invented anything here. I'm repurposing existing technology. It's innovation in the truest sense of the word. But the physical properties of ammonia are somewhat similar to LPG, liquid propane gas. So at ambient pressure, it's a liquid about minus 32 degrees C. Okay. So small tanks tend to be refrigerated. Large tanks tend to be refrigerated, atmospheric pressure, large tanks refrigerated. At ambient temperature, it's a liquid about 8 to 10 bar. So the small tanks tend to be pressurized. So it looks like an LPG tank. Okay. And it's very achievable. So the test site that I've been talking about, so we've built ammonia. Yeah, exactly. So we've built an ammonia energy storage demonstration system in the UK near Oxford at the Rutherford Appleton laboratory. And that demonstrates the whole round trip from renewable power, hydrogen water electrolysis to produce hydrogen, air separation to produce nitrogen. We built our own Harbour Bosch synthesis cell. That was quite fun. I'm reinventing the wheel here, but it was, as an R&D engineer, it was great fun. It demonstrates the principle on the one site. And then I store the ammonia in a tank, and we've just got a pressurized tank, sort of 2 meters long. And we use the ammonia as a fuel in a combustion engine. So I bought a genset, basically, a methane 30 kilowatt genset, and we fuel it with ammonia. So at our test site, it was a small tank, liquid storage under pressure. The big tanks, so the commercial industrial scale ammonia storage facilities, 20, 30,000 tons. The largest I'm aware of is 50,000 tons of ammonia. And that's a concrete tank. It looks, again, it looks like LNG tanks, but LNG is much colder. It's 111 Kelvin, something like 112 Kelvin, I think. Whereas with ammonia, I'm only, 250 Kelvin. It's much warmer, minus 32, something like that. But they're similar sort of size, concrete tank. 50,000 tons is 50 meters in diameter, 40 meters high, and that'll store getting on for 9,000 tons of hydrogen, which is a useful amount. So now we're in the territory that is useful
if I'm a manufacturer, right, I use that type of a fuel stock. That's the kind of storage I'm looking at to run a factory.
Yeah, well, again, an example, so an SGT 800, if I fueled that on hydrogen, that would consume just over 4 tons of hydrogen an hour. 4 tons per hour. So the biggest gas turbine Siemens makes is the 9000 series. Yeah. That consumes, if I fueled it entirely on hydrogen, 40 tons an hour. So, you very quickly, so again, in the north of England, we got the Teesside, we got some salt caverns there. They've got about 800 tons of hydrogen in, at 40 tons an hour. I'm not going to do that sum in my head, but it's a few days.
It will run out.
Yeah, pretty quickly.
It's not there for the winter.
And that's one gas turbine. Yeah, if you think about a power station, that's gigawatts you need. So this is the issue with hydrogen. It's fantastic from the opportunity that it gives us to decarbonise these sectors of our energy industry that are really hard to get the carbon out of. But we need to find a way of storing and transporting it. And this is where ammonia and these other hydrogen carriers come in.
And in Siemens and in the industries, you talk about sector coupling, and obviously if you generate, you want someone to use it and whatever. And obviously with, let's say, ammonia, it's already used and it's seen as a fuel stock. This isn't going to happen overnight. It's not going to, Friday morning, everyone's running on ammonia or hydrogen or whatever. What do you see happening in the next 12, 18, 24 months?
So, again, one of the advantages with ammonia is that the technology we need to deploy this at scale is kind of ready. So, the large-scale synthesis exists. We need to think about ammonia combustion in gas turbines, I think, and there's some R&D work underway within Siemens and a lot of research in academic institutions around ammonia combustion. Ammonia cracking is something else that we need to look at. So this is the idea of turning ammonia back into hydrogen. So if you want to run it through a PEM fuel cell, for example, then you need to crack it back into hydrogen first.
So I'm basically using ammonia as a way of transporting it around.
Exactly, and storing it. And then if you want the hydrogen back, you turn it back into hydrogen. Yeah, and so and actually the energy penalty is, that process is about 90% efficient. And it's actually 90, it's actually much cheaper to go to ammonia, store it, transport it, and go back to hydrogen than try and store it as hydrogen.
All the way through.
Yeah, especially at bulk. So ammonia cracking is another thing that needs a bit of work. But in terms of what happens next, it all really begins with hydrogen. And the best example I can give you is what we did this year at the Siemens display at the Goodwood Festival of Speed. So this is again in the UK. Yeah. I don't know if you heard about it.
I did, yeah.
Yeah, it was publicised on Yammer and on Twitter, and Siemens Twitter feeds and so on.
Many of your colleagues that were there.
Yeah, exactly. So that was a very interesting project and very popular. And what we did there was we took a hydrogen fuel cell to the Goodwood Festival of Speed with a hydrogen tube trailer as our energy source, and we ran the hydrogen through the fuel cell to produce electricity, which then recharged all the electric vehicles that were on display at Goodwood. So people understand, I think, that battery electric vehicles in particular, so fuel cell electric vehicles too, but sort of less so.
It's not as common.
Exactly, yeah. You see more battery electric vehicles today than you do fuel cell ones. So we were recharging battery electric vehicles with hydrogen, and the advantage of doing that is that sometimes you can't get the electricity you need from the grid.
True.
So if you're grid constrained, and EV charging actually represents quite a significant load.
Well, it can. I might have a nicely balanced grid, and then 1,000 people get EVs, and I don't have a balanced grid anymore.
Yeah.
Because who's plugging in where and what?
Exactly. So I mean, here on the Siemens stand at POWERGEN, we've got a 22 kilowatt dual charger. So that one charging post is 44 kilowatts. If I have 10 of those, I'm 4 megawatts.
I need a bigger cable.
With 40 of those, then then you'll go quickly up into megawatt. Power demands, and that can be problematic from the grid. If you can get it from the grid, then
it depends. It's situational, right?
Yeah, exactly. So this is another way, and certainly at Goodwood, we were in a field. There was no grid at all.
There was no transmission line to hang a wire on.
Yeah. So what we were able to do there was actually displace some diesel generation, which is how they power the rest of Goodwood.
Yeah.
Bringing in diesel gensets and power the EVs using hydrogen produced from wind power in this case. So we had wind power providing electrolysis, the hydrogen sort of remotely, tube trailer to bring the hydrogen in, ran it through a fuel cell. The only byproducts are heat and water, and we charged we charge the cars up. And this is a commercial application that works today. And the beauty of it for Siemens is that example is something that Siemens can pursue really with a lot of advantages. We're able to cover the whole end-to-end. We do the wind turbines, the electrolyzers, power distribution, transmission, and so on. We're going to partner, so at GeoPura we partnered with at Goodwood we partnered with GeoPura, a company called GeoPura. We need to think about hydrogen logistics, but then at the other end of the spectrum, releasing power from fuels is very much what gas and power do. And then we've got the whole smart grid, EV charging infrastructure bit with SI and mobility. Yeah, exactly. So we can, and we can kind of match the production of hydrogen with the demand from these EV charging posts, and kind of start from a very small base and scale it up. What will happen over time is that people will then bump into the problem with, well, hang on a minute, I'm shipping in 2-3 tube trailers of hydrogen a day. And then I can go, well, I've got a solution to that too, and we can switch over to ammonia and crackers and bring in just one trailer of ammonia. Yeah, so a similarly sized trailer with ammonia on it would have 4 tons of hydrogen, whereas a tube trailer that we had at Goodwood was 230 kilos of hydrogen. So it's yeah, exactly. So what we're proposing as a strategy is start with hydrogen, start with mobility because the prices are highest there for the energy, scale up from there, and then as the deployment comes up and we see some, we're here looking at, so here this is the Siemens electrolyzer, the latest products, the 300. This one's 17.5 megawatts, and you can, they're modular, so you can scale up from there. So then as we deploy at scale and the per ton costs come down, and then we can start looking at other industrial users and power generation when the costs are low enough. Because at the moment it's really an economics problem with hydrogen in power generation and particularly heating. So start with hydrogen in mobility, get the hydrogen economy going, scale it up from there, get the costs down, and then move out into the rest of the industry. And as I say, PowerTech is so exciting because so far we've looked at decarbonising 20% of our energy use. We're doing pretty well, and here's a market that's the rest of the energy is 80%. So it's potentially it's huge.
And as you say, it's not that you have to revolutionise the other 80% of all those industries with something completely new. They're used to using some of this stuff already. So
exactly.
It's not,
we're shipping energy around as a fuel, which is what we've been doing for decades. The fuel has changed, but the fundamental technology hasn't or doesn't need to. And this is an important message to get across within Siemens. Gas turbines,
they're still a gas turbine.
We used to still need gas turbines, and we're really good at gas turbines.
And the generator at the other end.
Yeah, exactly. Yeah, exactly. And this means that what Siemens is already good at, has a future. We don't need to change the technology. We need it so much as change the fuel. And as I say, we're very good at gas turbines. The efficiencies are fantastic. The footprint and the power generation. The megawatts you get out of them, they're going to be around for a long time.
As you say, it's the Power-to-X. It's about changing the fuel source as opposed
absolutely. Change the fuel, not the technology. Yeah, exactly. And as a, from an engineering perspective, this is fantastic because, it's an exciting technology challenge, but it has the potential to make a real difference to, the way we live our lives and the effects it has on our climate. As I said, I come back to my point right at the start. Energy is a good thing. We want to keep providing energy, but we need to do it in a clean way. So I can have a great time at work, developing this stuff and deploying it, but also know that it's secure in the future. Yeah.
And chatting with one of your colleagues this morning and a couple of weeks back at another event with Siemens Gas and Power, you've got the whole Making Energy Greener radar.
Exactly.
Power-to-X and going to decarbonisation, and these are all key bits of the puzzle.
Absolutely, and we need them all. It's a faceted approach.
It's not just this is the answer.
No, there's no such thing as the answer.
It's that easy.
Yeah, because and the energy market's huge, right? It's a massive industry.
And your point earlier in that what works in one geolocation may not certainly work in the other. Who's got salt mine? It's complicated, but yet the technology, the sector coupling, whatever.
We're going to need a variety of technical solutions depending on particular circumstance. But Siemens is very well placed to, deploy those as appropriately and have a sustainable business going forward. So
it's a fascinating topic.
It's very exciting.
Thanks a lot. Cheers, Ian.
A pleasure.